Now let's talk about tangent planes. It says let S be a surface defined by a differentiable function z equaling f of xy. And let p naught be x naught y naught be a point in the domain of f. Then the equation of the tangent plane to S at p naught is given by this equation here. Now keep in mind this equation here is a plane. It says tangent plane, but more so a plane. So if you remember the definition of a plane, this is the definition of a plane. I'm looking at the one below here. Now what I want to do here is I want to just take this equation here and I want to write it in this form down here, because remember, this is still a plane. It's a special plane, but it's a plane. Okay, let's move the z over to the other side, and I'm just going to rearrange this a little bit, but I'm going to write it near the definition of the equation of a plane. So then this would be f. So what I did here is I just rearranged it, moved the z over, and I have it equal to 0 now. Now it's very similar to the formula below with one exception. The one exception is here with the z component, but we really have that here. If I factor a z out of these, not a z, but a negative out of those two terms, and one more thing to understand here, realize that f of x naught y naught is really z naught. So what that does for us is really, if I pull that negative out, it's going to be a negative, and I'm going to have a z minus z naught equals 0. So now let me write the rest of this now. So that's what we're really looking at here. Now one thing to understand from this is notice that the f of x naught y naught and the f of y naught are actually the a and the b respectively. So here's my a, here's my b. And notice my c here. It's really like I have a 1 there. So my c is actually 1. So that's what's interesting about this formula here. It's a tangent plane. But one thing I can get from this more is that fx x naught y naught is my a, fy x naught y naught is my b, and then my c is negative 1. Now what that means is, and if you remember that, that's going to be my n. Now this isn't exactly right here, but this kind of gives me a gist of what I'm dealing with this tangent plane as far as my normal vector is concerned. And we see that here in the definition. And that's my a, b, and c, if you didn't remember. So there it is. So that's really what we're looking at here above. So that's a nice handy tool to have there, and just to understand that idea of what fx, x naught y naught, and fy, y naught, x naught y naught are, and then the negative 1, and where that comes from when we see these. It makes the problems a lot simpler when it's asking us for certain information. So that's the smaller idea. That's the details. Now let's take a look at the bigger picture here. So this is the bigger picture of what we're dealing with here. This is the general definition of a tangent plane. And it says let p naught equal x naught y naught z naught be a point on the surface S, and let C be any curve passing through p naught and lying entirely in S. Now S is the surface here. And if the tangent lines to all such curves C at p naught lie in the same plane, then the plane is called the tangent plane to S at P. And this is a nice picture of this, where you see the tangent plane here, and here's the surface. So again, if that curved surface there, the further I go out from that point, the more accurate it will be if I'm using this as the linear approximation. And in general, that's a big part of what we use that for, is for the approximations, because it's a lot easier to approximate with planes and lines and those kind of things, as opposed to like the curves themselves. So this is where it becomes a little interesting for us. So let's take a crack at that first problem that we've seen on the next page. All right, here it is. So here's our problem. It says find the equation for the tangent plane to the surface at the indicated point z equals e to the 7x squared plus 4y squared, and the point is 0, 0, 1. So now you can easily see what we need here if we're going to find n. And n is our normal vector that we can use for any plane, right? If we find that normal vector to the plane, then all we need is a point on the plane, and we have that with this here. So we just really need that normal. So to get that normal, we can take our partials with respect to x, so f of x. So my f of x then is going to be this function here with respect to x. So the derivative of e to the x is e to the x. So it's going to be e to the 7x squared plus 4y squared times, because there's a chain rule, I have to take to the derivative of the inside, and that's going to be 14x. And to clean that all up, and again, I like to go through those steps on those, just for the fact of getting used to these derivatives again. 7x squared plus 4y squared, and that's the first one, that's fx. Now keep in mind what we're doing here. We are looking for fx, x naught, y naught, and here's our point of interest there, so it's 0, 0, 1. So I can plug that in here. So my x is 0, my y is 0, and my z is 0. My z is 1, excuse me. But I don't have any z's here, so I'm just going to have 14 times 0, e to the 7 times 0 squared plus 4 times 0 squared. And I just put it all in there so you can see it. And we're going to just get a 0 there anyways. Because as soon as I seen the 0 here, I knew it was 0. So fx is 0. So let's take a look at fy now. So fy is going to be the derivative of this one as well. So derivative of y is, so that's going to be 7x squared, because e to the x is e to the x, times the derivative of the inside, and that's going to be just this y component. Now keep in mind, I don't have to worry about the x here because the x is a constant. I didn't mention that in the first one. So I just have to worry about this 4y squared because that's where my variable y is at. So that's going to be 8y. And like the first one, that's why I only ended up with a 14x, because y is considered a constant here because it's with respect to x. Okay, I should have mentioned that, but that's good. You can see it now. So this is going to be 18y. Oh, and I wouldn't say equals here. I would say implies. Okay, so this would be 18y. 8y. There, fix that again. Okay, and this is going to be e to the 7x squared plus 4y squared, and that would imply that I'm going to get 8 to 0 e to the 7 0 squared plus 4 to the 0 squared, which equals 0. So my fx and fy are both 0. And I have a point on my plane as well. So let's just write all that in here now into our handy-dandy formula. And one other thing we're going to need here is we are going to need one more piece of information here. We're going to need f of x naught, y naught. So we're just going to have to plug that in to our function here. So we're going to have to plug in 0 there. So that, and honestly, we have it. We already had it. It's going to equal 1 because this is 1. That's my z value. That's all it's really saying, is that my z is 1. Okay, so let's put all this together now. So I have z equals, now my fx naught, y naught, that's 1. That's here. And then I have my fx naught, that's here. So that's plus 0. And then I have my x minus, and my x naught is going to be this 0 here. So that would be minus 0. Plus, now my fy, x naught, y naught, that's this one here. Okay, so that's times 0, or plus 0, excuse me. And that's going to be y minus, y naught. Now my y naught's going to be here. It's just my point. That's my p naught. That's where it comes from. So minus y naught. And that's all my information I need for this. And when I simplify this, I get the plane z equals 1. So there's our answer. That's my plane. So we just did our first tangent plane here. And then you kind of get the idea that, hey, if I think about this, z equals 1, that's a horizontal plane. So whatever surface I have here, it's just going to be straight across at z equals 1. So we can kind of get an idea of what that means.